Okay, so I think we can start. So once again, welcome to this new webinar. And today's webinar topic is understanding the problem of strain localization and the concept of fracture energy regularization. This topic is very important whenever you try to model materials like concrete or masonry or any kind of material that shows strain softening. I will show you why you need to pay a lot of attention when you model this kind of materials. It is not so obvious, and if you do not take care about the problem of strain localization, you can obtain also garbage results. I mean, you have to pay attention to this kind of problem. So I will share my screen. Full screen. Okay. So basically, this is the contents of the files we are going to create today, and it will be available by tomorrow on our website. So I will try to introduce the problem of a strain localization due to damage. In this case, we are going to talk about concrete, but it is true for any kind of material that shows strain softening. So when the strength decreases with further straining. I will introduce the problem with the example number 1, which is called strain localization truss, because it is a 1D problem. Okay, so the simplest problem to show this kind of issue. Then I will talk about the same problem with beam elements. So what happens when you have a more complicated finite element formulation with also bending, so it's not anymore a 1D problem. And then I will move to continuum elements. For beam elements, I will also talk about the differences that there are between displacement-based and force-based elements when it comes to handling the problem of strain localization. So just to explain briefly before we start the problem of strain localization, I will try to explain you with a drawing here. So the main issue is basically that, so imagine you have a 1D problem like this. So you have 3 nodes and 2 elements, okay, which are connected in series, like a truss problem. So you fix here and you push here with a certain force, okay. Now imagine the cross section is 1, so the force is actually equal to the stress, okay. So divided by the area, which is 1, so it is the same. Okay, so now if any material here shows strain hardening, there is no problem. All the standard rules of finite element work because every material here, it has a stress-strain relationship which goes always in hardening. It's always able, if you have here stress and strain, every material point is able to transfer increasing stresses to the next element. Okay, so the deformation will always be smooth along the element. Now, in this case, it will be constant. Now, the problem when you have strain localization instead, let's go back to the same example, is that whenever the kind of material model, for example, is something like this, so linear elastic up to a certain point. Once again, here we have stress, and here we have strain, and then you have softening. Okay, so it goes down like this. Now, the problem is that imagine this kind of problem. Once again, this one is fixed. Here we have a force applied. They are elements connected in series. So what happens is that when one of them reaches the peak strength, like this one, now imagine one of them is slightly weaker than the other, because in reality, the distribution of strength parameters and stiffness parameters are not exactly the same, so there are imperfections. So one of them will be weaker than the other. So this one will go in the softening regime. Okay, so this one is the path followed by element 1. This one is element 1, and this one is element 2. Now, since they are connected in series, for equilibrium, the other elements should have the same stress. Now, the problem is that when you are in strain hardening, there is no problem. Okay, imagine like this. So the first element goes here. It is here element 1. The second element should be at the same stress, but there is only one point. So there is a uniqueness of the solution. When you have strain softening, there is not such a uniqueness of the solution, because for the same stress, the other element can be either loading like this, like the first element, or unloading, okay? Because both situations can give you the same stress. So it will be in equilibrium with the force here. Now, typically what happens is that some element is weaker than the other because there are imperfections in a real life structure. So it happens that one element shows a crack and the other element unloads, okay? So this one is element 1 and this one is element 2. Now, what's the problem here is that I imagine a slightly more complicated constitutive model like this. So something you have first an elastic response, then you have strain hardening. Up to here, the response is stable. And then you have strain softening, okay? As we said, one element develops a crack and it goes here. The other element instead should be in equilibrium, okay? So same stress, but it will unload, okay? So imagine you have an unloading path, which is a secant, which is secant like this. So the element 2 will be here. What happens is that now we have this first area, that is the energy dissipated by both elements, okay? Element 1 plus element 2. But all this area here instead is an energy dissipated only by one element, only by one finite element. This one will give problems, okay? I will show you through some examples why the concept of having this energy that is dissipated only by one element can give a lot of issues, okay? So let me clear everything. Let's go to the example. Basically, it will create two kinds of issues, okay? So as I said before, you have one issue, which is the non-uniqueness of the solution, okay? So one element load and the other element unloads. And this is very difficult for the numerical model to understand which element should load and which should unload, because in reality, you have imperfection. But in a finite element model, you have a uniform distribution of properties. So that one will be the first problem, which is called bifurcation of the solution. The solution is not unique. And the other problem is the second one that I showed you. The amount of dissipated energy will depend on the finite element size, because as you have seen, since the elements are connected in series, only one of them will dissipate energy, while the other will unload elastically or with a secant matrix or whatever. So only a small portion of the energy will be dissipated by all the elements, but all the other energy up to the complete formation of crack will be dissipated only by one element. Now imagine that this energy being dissipated in only one finite element, it means that the total energy dissipated by the system will depend on the finite element size. And this one is the second problem, okay? So I will show you how this kind of problem can happen in your model and how you can handle it, okay? So first we will start with this simple truss example. So you will be able to open a file called 01 strain localization truss. And here what you have is, let me go back to a grid of one. Oh, in all this example here, I'm using kilonewton and meters for the first two examples. And the last one instead is a small specimen. I will use megapascals. Okay, so basically here what you have, what we have is 3 trusses. Okay, let me go back to the XY plane. 3 trusses. Okay, so you have just 3 geometries. Then here we have 3 selection sets. I need them just to monitor the output. Okay, so for example, let me go to the mesh here. You will see that I created 3 different meshes. Okay, this one has a mesh size of 1, 0.5, and 0.25. Okay, so each one is half the size of the other. And so this one will be the fine model, the medium model, and the coarse model. Okay, so here we have the selection sets. Coarse is the point here, the loading point of the coarse mesh. And then, of course, we have here select the control point of the medium mesh. And here we have, oh, this is the same thing, fine, select. And here we have the control point of the fine mesh, okay? We have just one definition, a simple linear ramp, because we are going to apply just a monotonic imposed displacement. Okay, and then we have a constitutive model for concrete. Okay, here we are using the damage TC1D. You can use any other model. Here we are going to use this kind of model because it is much easier to perform the regularization. Okay, you have seen this model in other webinars. So we have the Young modulus, the tensile strength. This one is the fracture energy in tension. And then we have the properties for compression. Okay, so this one is the stress at the peak, at the elastic limit. Then we have the stress at the peak and the residual stress. Then we have the strain at the peak, compressive fracture energy, and then a few other parameters that are not important here. Actually, we are in this kind of model, we are just going to perform a tensile test. So only these two parameters are important here. And then the auto-regularization stuff, this is very important. Then we have a truss material, because this one is a simple stress strain law. We have to convert it to a truss material, which is the material plus an area, basically. Okay. And then I also added a small piece here, which is, let me show you this one, which is elastic. Okay. The reason why I made it elastic is just to avoid some numerical issue with imposing a displacement on a material that can damage. Okay. But this is not important for the topic of we're going to talk today. Then we have the truss element and the boundary condition. We have a fixity here of the X displacement, so the first degree of freedom. And then we have, for all the elements, we fix the other 2 degrees of freedom. Okay, so we make this problem 1D. And finally, we have the load, which is actually here on the 3 endpoints, which is an imposed displacement of 0.002. Okay, so 2 millimeters. And then here we have a small script. I will talk about this later on. So let me switch it off and I will explain you what it is. Then we have the recorder as usual. So now do not focus on this. Imagine this one is not here. So you start by the recorder, then you have boundary conditions, then you have the imposed load, and then we have the 3 monitors. Okay, one monitor will monitor the displacement, the force displacement of the first truss, the second truss, and the third truss. Okay, and finally we have a simple analysis. Okay, so static analysis, no special stuff here. Okay, now let's start with how you would represent this model without knowing anything about the problem of fracture energy. Okay, so imagine you don't know anything about fracture energy. You do not switch on regularization. Okay, so for you, you don't know about the problem of fracture energy, of non-uniqueness of the solution, and you forget to use the regularization because you don't know what it means. Okay, so you start like this, and I will show you what is the problem in this case. Okay, so let's start with this one, and also without any imperfection. Okay, the imperfection is 0, so this piece of script will not be executed. Okay, this is a plain problem. So you define a stress strain model with strain softening without taking care of regularization, and you apply this one on 3 different meshes. Now, from the theory of finite elements, you know that once you refine the mesh, you converge to a unique solution. Okay, so the solution will be better here, and from here it will be a good approximation, a better approximation, let's say the best approximation. But the thing about finite element is that you can rely on the fact that refining the mesh, you will go to an exact solution or a unique solution. This is not the case with strain softening. Now we will see that. So let's start by running this analysis. And let's see what happens. Now, if you run this one, you're going to have a convergence problem here. So let's plot all of them, coarse, fine, and medium. Now, to understand what's going on, we need to zoom here. Up to here, so up to the tensile strength, okay, everything is fine. But then all the elements go into the softening regime. As I said before, in theory, only one element should go in softening, the other should unload. But the problem here is that all of them are going into softening up to a certain point. Okay. up to here. Then here something is happening. Basically, what is happening is that during the Newton iterations, the iterative scheme is introducing some error somewhere. So some element will start to unload and the other will start to loading, okay? And this is what happened. Up to here, the OpenSys is trying to reduce the time step, but it cannot find convergence. It's very difficult. Why? This is called the problem of bifurcation. So we have a problem of a perfect uniform distribution of material properties. So all the finite elements have the same strength, same stiffness, same everything. But also the kind of problem is a constant state of stress. So you have uniform parameters, uniform material parameters, and a uniform deformation. So it's very difficult for the numerical method to understand what is the element that should fail, because all of them have the same strength and the same stress, okay? So up to here, all of them manage to show a certain damage, and then here, the numerical model is failing to find convergence. Now, to understand what's going on, you can go in post-processing. Now, what you will imagine is that in real life, if you apply a tensile stress on a concrete bar, you will see a fracture somewhere, but the fracture is very localized, only at a certain point. Now, here, instead, it is not like that. So if you open this one, and you open the problem of trusses, and we try to show the damage, material damage, and to show the damage, I want to change. Okay, here you can see, and we put 0 here. Okay, so you can see that all of them has a certain damage. So some of them, actually, we can go slightly here. Okay, up to this point, all of them show a 0 damage. Then they reach the peak strength, and they start showing some damage. But all of them have the same damage. Okay. In fact, if I switch off the minimum, you can see that all of them has the perfect same amount of damage up to a certain point. So towards the last point, some element will start showing an increasing damage. But as you can see, it is very unstable. If I try to run this one, you will see all the damage flickering around here. Look here, 0. Then they all proceed to the same damage, and then there is this kind of numerical error up to non-convergence. Why? Because, as I said, you have a constant state of stress, a constant distribution of properties, and the numerical solution simply doesn't know what solution to get. Okay, so all the elements can be damaged, only half of them, only one of them. So you have a multiple solution. Okay, and this is called bifurcation of the solution. It's pretty much like in buckling, for example. If you have a perfect straight column and you apply the critical load, the column will not buckle unless you insert some imperfection. And here for damage, it is the same thing, okay? So the first problem that you have to solve when you have this kind of benchmark problem, so when you have constant state of deformation, is to introduce some kind of imperfection. Okay, now, for example, in this case, I did it with a simple script, Tickle script, by changing the area of some elements. Now, if I turn on imperfection, and I will explain you this simple script, what it means. So if this flag is set to 1, okay, I go inside this loop. Oops. This one is an OpenSys function to get the IDs, so the tags of all the elements. So I say for each element tag in all the element tags in OpenSys, and for each node of the nodes of this element. So this one is another OpenSys function that gives all the nodes of this element here. Then for each node tag, I can get the position of the node. I can get, and this one is an array of 3 components, X, Y, and Z. Then I can get the X component by just taking the first index of this vector. And then I say, if this node is approximately at 0, I want to add an imperfection to this element, okay? So the concept of this script is that I want to make all the first elements, so the one near the fixity, slightly weaker than the other. And to do so, I just use the parameter concept in OpenSys. So I create a parameter, I add this element to the parameter, and this parameter is linked to the area of the truss, okay? Then I get the current value of the area, which is A0 with the get parent value. Then I compute the modified area, which is 0.99, the initial area. So just a 1% damage applied here. Okay, so the area is reduced by 1%. And then I update the parameter. So what it means is that when I run this function before running the analysis, the first elements, so this one, and this one, they will be slightly weaker than the other. And now you will see that these will improve very much the convergence. Okay, so we solved the first problem, but you will see the second problem now. Okay, so let's see what happens now with the imperfection turned on. I run this and I switch on all the plots. Okay, so now you have a pretty good convergence. You don't have any problem of convergence. 3 iterations, one, of course, here when it is elastic, and then 3 iterations. Now, if we look here, all of them reach the point here, and then they start unloading. But here you have the second problem. You expect all of them to have the same solution as in the elastic part, but instead, when they reach the point, the maximum point, the 3 models, they show completely different solution. More specifically, you see that the coarse mesh is more ductile, while the finer mesh is more brittle. Why? Because as I said before, if you have a solution like this, let me do a drawing. Because now we have okay, imagine you have the first element, which is this one, then the second element is smaller, okay, and then you have the other meshes. This one is failing, but also this one, okay. So they have the same stress strain law. So imagine they have the same sigma epsilon. So this one is the specific fracture energy. This one will be integrated over this length and over this length, okay. So it is clear that the coarser mesh will dissipate more energy because we have the same specific energy for a larger volume, okay. This is exactly why this is exactly the reason why you increase the mesh, instead of going toward a unique solution, you go toward a even more brittle solution, up to a certain point that when your mesh will be too fine, the solution will be extremely brittle, okay? Up to a limit when the solution will try to have a snapback, but it can't because we are doing a displacement controlled analysis. Okay, so the main problem is that here, this one is not good in finite element, because you know that you rely on the assumption that refining the mesh gives you the correct solution. But in this case, this assumption does not hold anymore. So here we need to solve the second problem, which is the dependence of the solution on the mesh size. Remember that the mesh is just a tool, a numerical tool to discretize a problem, but the solution should not depend on the kind of mesh that we use, okay? At most, we can say that the finer is the mesh, the better is the solution, okay? But the solution should converge to the same problem. And with strain softening, this does not happen. Now, in literature, there are many techniques to solve this kind of problem, like non-local models, integral models. They are quite complicated, but the regularization of fracture energy is the easiest one. It can be implemented in any kind of softwares, and we have it in OpenSys. Now, how do you solve this kind of problem? Okay, so the concept is that whenever you define a material model that has softening, you should introduce a fracture energy as the area underneath the stress displacement curve, not the stress strain curve, okay? So once again, imagine I have from experimental test, they told me that this concrete behaved like this. So they did a tensile test on concrete, and then they gave me a stress versus displacement jump curve, okay? And then I have a curve like this. This area here is called fracture energy, okay? In this case, it is for tensile, the tensile response, and this is called GP. The fracture energy is the amount of energy required to open a crack of unit area. So it actually has the dimension of a work, okay? So for example, it can be joule over meter squared, okay? But this one is actually a force times a length. So force times a length over an area over a length squared. So it turns out that it has the same dimension of a stiffness, okay? So force over length. If it is the area underneath the stress displacement curve, okay? So if you have this, now in this first example, let's assume that you have this kind of quantity, okay? They did some experimental test on concrete and they gave you this kind of experimental output, okay? So from this diagram, you can get the GT. Okay, if we have it, we can simply put it here, GT, and the same thing for the compressive behavior. And then we simply have to switch on the automatic regularization. Now, this kind of material model has an automatic regularization. If you use another model that does not have this kind of tool, you can do it manually. So what it is doing is described here. So when this flag is true, which is the default, by the way, the input fracture energy, GT and GC, will be divided by the element characteristic length in order to obtain a response which is mesh size independent. What is the characteristic length of the element? Once again, well, there are many definitions for characteristic size, but typically it has the dimension of a length. Okay, so imagine a perfect square element. The characteristic length can be this one. If you have a triangle, it is this one. Now, you may, if you go in literature, you may find papers that say, okay, but the real characteristic length is actually the size of the element orthogonal to the crack. So imagine you have this kind of crack here. Then the characteristic length is the size of the element in the orthogonal direction of the crack, okay? Now, it is very complicated to compute the characteristic length based on the inclination of the crack. Okay? In OpenSys, it is not done like that. In OpenSys, the characteristic length of the element is the minimum distance between two consecutive nodes. Okay? So if your mesh is sufficiently regular, the mesh size, it is, for example, for a quadrilateral element is this one, and for a triangle is this one. Okay? So the height of the element. Same thing for 3D. So it always has a dimension of a length. For a beam element, same thing, is the distance between the only two nodes that you have. Okay, so the entire length of the element. This is called characteristic length. Okay. So let's clear everything. So here what you input is the real fracture energy, which is a value that is a force over a length. And then, because actually what I said is a force over a length, it's actually it is the area underneath a stress displacement curve. Okay. What this software does is that if you turn on automatic regularization, then each material point get the length of the parent element and say, okay, but now I change this value from this value, compute the specific fracture energy, GT, which is equal to the real GT inputted by the user divided by the characteristic length of the element I've been assigned to. Okay, so imagine you have 10 elements, you have 10 material points. Each material point will perform this operation with its own characteristic length. Okay, so it is very convenient to do it with the automatic regularization. Doing it like this, you have a specific fracture energy, which is specific to that element. Okay, and so in this case, since you divide it by the length, it turns out to be the area underneath an equivalent stress-strain curve. Okay, so this one will be GT, which is equal to this GT here divided by the characteristic length of the element. Okay, so if you use this material model, it's very easy. You input the real fracture energy, force per unit length. You turn on automatic regularization, and OpenSys will do everything for you. Okay, so this material model will perform this regularization automatically. If you don't have this kind of material model, you use another material model, like for example, the concrete O2, okay, where instead of inputting the fracture energy, you input the ultimate strain. then you should do the regularization manually. Okay. For example, you have two different mesh sizes. You get two different materials, and if a mesh size is half the first one, the second material will have an ultimate strain which is twice the first one. Okay. But if you use the concrete the damage TC1D, it will be much easier. You just need to switch on this. Okay. So now what we have the imperfection to solve the bifurcation problem, and then we have the fracture energy regularization to solve the mesh dependency problem. Okay. So now let's try to run this analysis again with these settings. Multiple elements, and now you will see that all of them give the same response. Okay, and this is what we want to do. Okay, we want to make sure that the solution is independent of the mesh size. Okay, now if we go back here, okay, and we reload this one, we will see that now the damage is only here. Okay, we start from here, no damage, we reach the tensile strength, and then we start developing damage at the first elements because I assigned an imperfection there. Okay, up to the very end. Now, to understand what the regularization has done, we can look at the Gauss plot here. If we go on Gauss plot and we try to extract the stress displacement curve of this element, then this element, and this element, you may think that all of them will show you the same stress strain curve because you assign the same material, but instead they will give you different responses because of the automatic regularization. So if I try to export the stress strain now from stage 1, material strain versus material stress, next, keep multiple results. Okay, you will see that they are different. The black one is the first one that I selected, okay, which is the larger element. The fracture energy regularization has decreased the input fracture energy because then he knows that it will be dissipated on a larger element. Okay, so this one has a smaller specific fracture energy, but it will be integrated over a larger element. This one instead has a slightly higher fracture energy, but it will be integrated on a smaller size, and so on. Okay, so what the fracture energy regularization is doing is changing the material point parameter, in this case the fracture energy, to make sure that the global response is the same. Okay, while instead, for example, if we turn it off, you will see something different instead. If we turn off regularization, what you will see is that here you will see the same stress strain curve, but the output will be dependent on the mesh size. Okay, so we run it again. So a wrong global response. Okay, so the response, the global response in terms of force versus displacement depend on the mesh size. Why? Because all the elements now, all the elements have the same stress strain curve. Okay, what it means is that if they have the same stress strain curve, then they dissipate the same amount of energy per unit length, but this one is the double of this one, and this one is the double of this one. So this one will dissipate more than this, and this one will dissipate more than the other. That's why the global response instead, which is this one, is different. So locally it is the same because I'm using the same element, the same material model, but globally it is different because the solution depends on the mesh size. Okay, so the topic here is that you always have to use fracture energy regularization. So once again, I go back here and I run the analysis. Okay, so basically this is the kind of problems that we have, and represented by a simple 1D problem. I will show you that the same problem happens in beams, same thing, okay? But I will show you another problem in bending now. Okay, so this one is the example that you find on fracture energy. Now we can move to the second example. So the second one is the strain localization in beam elements. Now let me explain you what we have here. Here we have 6 columns, and here I want to close the output. So here we have 6 columns, and I named them like coarse displacement based, medium displacement based, fine displacement based, and the same thing, coarse, medium, and fine, force based. Okay. Once again, I have 6 selection sets. Each one of them will be the top node of the corresponding element, because I will monitor all of them. So I will have 6 monitors, 3 for the displacement based and 3 for the force based. Okay. And then I have some concrete models. Then I will explain you why I have one for displacement based, one for force based, and so on. But let's start with a simple wrong approach. Okay. So we define only one constitutive model without regularization, okay, with the real fracture energy. So imagine that from my experiments, I have a fracture energy of 0.2 and 80, but I forgot to use the automatic regularization, okay? So what I expect here is that each mesh will show a different result. But then I use in the fiber section, for all of them actually, both here, this one is the fiber section for the displacement based, and I'm using the displacement based material. And this one instead is the fiber section assigned to the force based columns. Now let's start with the same material model. So we'll use the same concrete as before. Okay. So this is what you would do if you don't know the problem about strain localization, displacement versus force based element. So typically what you would do is to create a single concrete, a single fiber section, and you assign them to all the elements. Then 3 of them will be displacement based and 3 of them will be force based. Okay, these ones here. And as I said before, you have different meshes. Okay, so the first one has a mesh size of 1, 0.5, 0.25, and same thing for the other. So here what you have is a single material model without any regularization. So same material model, but applied on 3 different meshes and 2 different finite element formulation. And this is what will happen. Well, of course, then you have boundary condition, you have a fixity at the base, you have a constraint to impose a 1D problem in the XZ plane. Then you have first vertical load and an imposed displacement, okay? And then you have a 2-staged analysis. The first is a gravity analysis with the vertical load, and then you apply the horizontal load, okay? So also here, let's try to run the analysis and let's see what happens. If I run the analysis as it is, and I plot all the monitors, I will see a stable solution up to the hardening point and then a mess here. Now here I'm going to have, also convergence problems. Now, as you can see, you're using the same material model, but for 3 different meshes with 2 different finite element types. So you have 6 different columns, and each one of them is showing a different output after the peak point. Okay, so the solution is stable with strain hardening, and up to here the concept of finite elements work. But after the peak point, then the concept of refining the mesh does not hold anymore, and you obtain 6 different responses. Some of them are so brittle, like this one, that the convergence is not even possible, even with a very small time step. Okay. So what we have to do now? The first thing that we have to do, as you have learned from the previous lesson, is that you need to regularize the fracture energy. Okay. So you may think of, okay, I go in this material here and I simply turn on automatic regularization. Okay. You may think, okay, this is fine because I have to normalize the fracture energy with the length of the element. Perfect. Then I run the analysis now, and let's see what happens. As I said, the characteristic length in OpenCs is computed as the length of the element, okay? Also for beam elements. Now, what you see here, let me change the color. Okay. What you see here is that now the solution seems to be regularized, but in two different groups. Now, let's wait for the analysis to finish to understand what's going on. Okay, now here, up to here, we think we have, yes, convergence problem also here. Perfect. So once again, up to the peak point, everything is fine. The solution is the same. There are small differences, but it makes perfectly sense because the example that I did before, it was a constant state of deformation. So even one single element can give you the exact solution. Here it is a bending problem with nonlinearity, so it is not the same thing. You will see a small difference, but the solution is stable. Actually, as you refine the mesh, they go to the same solution. But when you reach the point now, you have a regularized response for these three are the three force-based elements. So the green one, for example, if I switch off displacement base, and displacement base, you see that the force-based elements are correctly regularized between them. Okay, and same thing for the course-based. Sorry, for the displacement-based. I switch off force-based. Okay, so they are regularized. Same thing. The force-based are better regularized because they are more accurate. Here there is, you need to divide a lot the element for the displacement base, but the concept is the same. So as you refine them, you go to the correct solution, which in this case was about 100. But then after the peak, the solution is unique. Now the problem here instead is that we don't have the same solution between force-based and displacement-based. So why is this happening? Because what I said before is that let me do a drawing, annotate. So this one is our finite element. So as I said, in OpenSys, the characteristic length is defined for every kind of element as the minimum distance between two consecutive nodes. Okay, so for a beam element with two nodes, this is the characteristic length. Okay, LCH. And it is the same for displacement-based and force-based element. But now there is a problem. A displacement-based element, this kind of definition for characteristic length is fine for a displacement-based element because a displacement-based element assumes a pattern of deformation. Now, in this case, it is a curvature, which is linear. Okay, so all the points here, all the Gauss points will localize. In a force-based element, instead it is different. In a force-based element, what we assume is not the curvature, but the bending moment. Okay, so the bending moment is linear in this case. The curvature will be different. To have the same bending moment, but this point here, for example, is fracturing, while this one is not, you will see a very high deformation here and a smaller deformation to the other points. So the deformation is not imposed to be linear, it's not imposed to be continuous, but it can be discontinuous between the different Gauss points. So for a force-based, so this one is the displacement-based, this one is the force-based. For a force-based element, the characteristic length should be the length of the Gauss point, which corresponds to the weight of the Gauss point I times the length of the element, the LCH element. And this one is the LCH for the force-based column. Okay. Now you may ask, okay, but how do I know what is the weight of the of this discretization? Well, you have to know that this kind of element. Let me switch off the drawing. First, you have to know how many integration points you used. Okay, so here we use 3 integration points for the force-based. Okay, now a Lobato integration scheme with 3 integration points, you can find them on the literature, but in this case here I have them in OpenSys. With 3 integration points, you have these weights here. Now in OpenSys, the weights sum to 2. Okay, so if you do the sum here, it will be 2. So actually, the weight, the smallest weight that I have here on the endpoints is 1/6. Okay. So if it is 1/6, it means that and my model will perform a regularization according to the entire length of the element. So imagine something like this. Okay, my finite element model will say that G small, so the specific fracture energy, will be equal to the real fracture energy divided by the characteristic length. Okay, but the characteristic length in this case, in my case, it is the entire height of the element. While for the force beam column, it should be LCH, should be the height of the element divided by 6 in this case. Okay, because for 3 integration point, the weight of the first integration point is 1/6. So what I should have here for a force-based element, GF force-based, should be GF, the real fracture energy, divided by this one here. So 6 times this divided by the height of the element. So this one is already done by the automatic regularization, but then I have this factor of 6 here, which is missing. Okay, so what I can do is that if I know this kind of problem for the force-based element, I can simply create a copy of this material model. Okay, so this one is the real material model that I would assign to a displacement-based element. Then I make a copy of it, okay, which is exactly the same, but the fracture energy are multiplied by 6. Okay, so you just have to remember, for example, if you typically use 3 Gauss points for force-based, 6 is the scale factor. So you put 6 here. Okay, you multiply the GT and GC by 6, and then the fiber section for the force-based will have the modified material: concrete for force-based, concrete for force-based. Okay, I simply have to do this, and both of them should be automatically regularized. Automatic and automatic also here. Perfect. And now I can run the analysis, and let's see if I manage to, this one I can switch it off. Okay, let's see if I manage to fix this problem. Okay, up to the point here, the solution is stable, and then here is where the two solutions were separating from, or going apart. Okay, now you can see that they've been stabilized. Okay. Of course, the solution is not exact because they behave differently. The solution is not a constant state of stress, but as you can see now, they are following the same trend. Okay. We have something in the chat in the meantime. Oh, yeah. Can you repeat where the 6 came from? Yes, I can show it now. So here is the problem. Why I had to change this material model, this one, as a fracture energy multiplied by 6. Why by 6? Because as I said, I'm using a force-based column element, okay, which has 3 integration points. Where is 3 integration points here? So the force-based element has 3 integration points. The force-based element localizes only on 1 integration point, okay? So it is not correct to assume that the characteristic length is the entire length of the element. Instead, for a force-based, the characteristic length should be the length of the Gauss point. Now, if I have 3 Gauss points with a Lobato integration scheme, I know that a Lobato integration scheme with 3 integration points has this number here is 1/3, okay? Plus 1/3 plus 1.3, they have a sum of 2, okay? I want to normalize it, okay, so that they sum to 1. So I simply have to divide this number by 2. And this one divided by 2 will be 1/6, okay? Now, if I come back here and I repeat the equation, if I know that the characteristic length of the element, of the force-based element, is equal to the real characteristic length of the element, so the entire size of the element, divided by 6, okay, then I go back to my equation and I say that the specific fracture energy for the force-based should be equal to the real fracture energy divided by the characteristic length of the force-based, okay? But actually, this one corresponds to GF divided by the real characteristic length, so the size of the element times 6, Okay, so this one goes up. Now, as I said before, if I go here on the concrete model, the automatic regularization is performed in such a way that the characteristic length is computed in the same way for each element in OpenSys. So the piece of the code that computes the characteristic length doesn't know if an element is displacement based or force based. So the rule is that regularization will perform only this part here. We'll take GF and we'll divide it by the length of the element. Now, since I know that I'm working with a force-based element, I have to perform this correction here. So I have to multiply it by 6 if I'm using 3 integration points. If I'm using 5 integration points, even more. Because in 5 integration point, for example, is already 1/6, but this one has a sum of 2, so it should be divided once again. So it should be 1/12. Okay, so if I have 5 integration points, I have to increase the fracture energy 12 times. So is it clear? I know it's a little bit complicated, but okay, perfect. It's just this kind of problem is only for force-based element. Any other element which is displacement-based, you can assume that the automatic regularization is fine. Only for a force-based, you have to account that the characteristic length computed by OpenSys is not correct for a force-based. So you can apply this correction by increasing the input fracture energy. Okay, so that's all. You just have to increase the fracture energy to account for the error made by OpenSys in computing the characteristic length of the force-based. Okay, so if you do so, as we said, the solution is unique. Not as unique as the Truss problem, because it was a constant state of deformation. But this one is fine for me, because in this case, I see that I have the same ultimate force, which is very precise for a force-based element. For displacement element is not so precise, but it makes sense because a displacement-based element needs many more discretization to reach the same solution. But what I like is that up to the peak point, I have the same trend. Okay, they dissipate more or less the same energy. So this is fine. As we said, the same problem that we had before, we have it now, we've solved it. If you notice, in this kind of problem, I didn't put any imperfection as I did in the previous model. Why? Because putting imperfection is only necessary if you're doing a simple benchmark problem, which has a constant state of stress. Now, in this case, it is not constant. It is a bending problem. So the curvature will be anyway. Once again, I do the drawing. In this case, I'm applying a force here. So the distribution of the bending moment is here. So it is not a constant state of deformation. The solution knows that these elements here are the ones that are going to localize first. Okay, so there is no problem of bifurcation of the solution in this kind of problem. So it is not necessary to put imperfection just for triggering localization. The localization will trigger anyway. Okay, so we can get rid of the point now. Okay, so as we said, we have the same problems here, and we can solve them in the same way. The only new notion that you have from here is that when you use the force-based element, you have to account for the fact that the characteristic length is not anymore the length of the element, but is the length of the Gauss point. So this is the only difference from the previous model. And now we can move to the last example, which is this one, strain localization on continuum elements. I decided to do this kind of model here. I'm going to show you what it is actually. So let me close this one. And let's open the third problem, strain localization in continuum elements. Okay, so here what we have instead is a compression test on a concrete cylinder. Okay, I'm going to explain you in detail what it is. But actually, it came from some questions that we have on our forum. by a user that was trying to model this kind of, that he had a nice problem, and he asked all these kind of questions. I don't know if you noticed, but up to the first two examples that I've done before, I always assume that you have access to the real fracture energy, okay? So sometimes it is true, sometimes it is not. Now imagine that you have some experimental test, and they give you the stress versus displacement graphs, okay? So from those plots, you can get the real fracture energy. But what happens if they give you the stress versus strain curve, okay? This is exactly what this user was asking. Now, if you're interested, you can go here into the post. It is under preprocessor property damage TC3D. You go to the very beginning, but basically the user was asking, from the Chinese code, I know that my specific fracture energy is 0.176 for that kind of peak strength. Okay, so for a concrete of a peak strength of 34.5 megapascal, the Chinese code was saying that the fracture energy, the specific fracture energy for a stress strain curve should be 0.176. Or imagine it is not the Chinese code in this case, but it is an experimental test, and they give you the stress strain curve. Okay. Now, typically, what they do is they prepare a test like this one, then they apply a force, and they measure a displacement. Now, imagine they measure the displacement throughout the entire height of the specimen. Sometimes they place LVDTs on a smaller section, but for simplicity, let's assume that they measure the entire displacement jump as the difference between the displacement at the bottom, which is 0, and the displacement at the top. Okay, and then they apply a force. Of course, what they obtain from the experimental test is a force versus displacement graph, which is something like this, and then they convert it into a stress versus strain by taking the force divided by the area here. And for the strain, they take the displacement jump divided by the height of the specimen in this case, okay? So you obtain a curve like this. And this area here, for this user, was 0.176. And then he said, okay, but if I apply this kind of number, I have a problem because it is already specific fracture energy, so I cannot regularize it. How do I obtain the real fracture energy to put inside my material model? We will try to see it, okay? So let's close it. And let's start with this example. This is how I explain to this user how to tackle this kind of problems. Oh, and basically what he wanted to do actually was to do something like this. Okay, I know that this is the curve I obtain if I input that specific fracture energy. And in China, the specimen is a specimen of 300 millimeters with a diameter of 150 millimeters. So he said, okay, I want to replicate the same experimental test and I want to obtain the same curve, okay? Which should make sense. So if they measure a stress strain curve like this, I apply it, I do the same experimental test, and I want to obtain the same stress curve. So I measure the force here, I divide it by the area of the cross section, then I measure the displacement, I divide it by the height of the specimen, and I want to obtain pretty much the same thing. But then he had several problems. He said, okay, but if I use the real fracture energy, it is too brittle. If I multiply it by the height of the specimen, it's too ductile, and so on. So he was a little bit confused about how to tackle this kind of problem. So this is how you can do it. Now, first of all, I want to explain you slightly the model. So this one is the concrete cylinder. So if we go into the geometry, this one is the concrete cylinder. Then we have a bottom plate and a top plate. And then we have an interaction in between, okay, which is this one. And this interaction is for imposing contact. You will see that in this kind of problems, the boundary conditions are very important, okay? So if you simulate a complete fixity, it will not be the correct solution, okay? Instead, you need to use a real contact where you can calibrate the friction coefficient. I will show it to you later on. So we have a body here in the middle, which is the concrete plate and the concrete cylinder. Then we have two steel plates. I have some selection set for the control node, which is a node here, which of course, since this block is rigid, this displacement is the same as this one. So I can change it also. And then the reaction set is the entire face at the bottom. Okay, so here I will compute the entire reaction. Then I have a simple linear ramp because I will apply reinforced displacement. Then I have a concrete model, and let's start by inputting the fracture and the specific fracture energy. Okay, so the one given by the stress strain curve of the experimental test. Now in this case, it was 0.176 for the compressive, and this one for the tensile fracture energy. And of course, he didn't use any regularization because he said, okay, I already have the specific fracture energies, okay? And then I will show you what is the problem of doing this approach. And then we have the steel plate here, okay, it's just a steel material. I will talk to you about what is this material model, but now I'm not using it. Then we have tetrahedron elements for the concrete, brick element for the two plates. As you can see, I discretize them only with one element because they are rigid anyway, so I don't need the deformation of the steel plate. And then we have a contact condition, which is this one, contact element, which has a very high normal contact and tangential contact, and the friction coefficient. What is the friction coefficient? I started with the friction coefficient that you can find between concrete and steel. So if you go on the website, you can find some stuff about concrete to steel friction coefficient or any other material. You can see that they go from 0.4 to 0.6, so it plays more or less 0.5. Okay, you can find on the web the different friction coefficient for different materials. And now let's see if this is correct or not. Okay, and then I have a fixity at the bottom, complete fixity of the steel plate. Then I have a fixity at the top on the X and Y component because I don't want the plate to move on the horizontal plane. And then I have an imposed displacement on the same top face of about 3 millimeters. 3 millimeters simply because when I am here, oh, actually what I've done here actually was to start from this material model. Okay, let's say the Chinese code tells me that this one is the fracture energy that I have to use, and I want to see what I obtain. So I go here, I push it up to 0.01 compression. This is the curve that I obtained following that code. Okay, so I went here in data, I extracted the epsilon 11 and the sigma 11, and I put them actually here in the monitor as a background curve. Okay, so I put them as a background curve. I changed just the sign, so I made them positive. And so in the monitor, what I'm monitoring is the displacement along the z direction of the control node divided by 300. Okay, because 300 is the entire height of the specimen. So from the displacement, I go to the strain. Okay, minus because the displacement is negative, I want it positive. Then the reaction. The reaction is the reaction force along the z-axis at the reaction set, which is the face at the bottom. Here I want to do a sum because I want to sum all the reaction, and this factor here is 1 over the area. So you can simply isolate this one. You go in geometry, query geometry, properties, I select the top face, for example, query area. This one is the area. Now, in this case, it is a cylinder. It's very simple to compute by the equation. But if the geometry is more complex, you can use this tool in STKO. 1 over this number will give me the scale factor I have here. Okay. So this one is what they do in experiment from passing from forces to stresses. Okay. So what I will obtain here is that I have strain in the abscissa and stress in the ordinate here. And I would like to see a response which pretty much resembles the background plot that I obtained from a precise one-point material model. And then I have the analysis, okay? Now in this case, I discretized the mesh a little bit. I created 6 partitions to make the analysis a little bit faster. Now let's see what happens if I input the specific fracture energy without any regularization and anything. So I go with OpenSysMP and I run the analysis. Now this is the background curve that I would like to obtain. Now the elastic response obviously is correct. Otherwise, it means that I made some mistake in the boundary condition. Then up to the peak point is fine. And now let's see what happens after the peak point. Okay, it's a very brittle failure. So it is not giving me the same answer. Well, what's the problem? Let's stop the analysis. The problem is that what I put here is the specific fracture energy, but according to an experiment or according to the Chinese code, but it is the same thing in this case. The point is that it is specific to what? This one was specific to that specimen. So it was specific to an object with a height, a characteristic length of 300 millimeters. Okay, so I cannot put it as it is here because I can obtain a good result only if I have one element through the height of the specimen. But of course, this is impossible. So what I have to do here instead is to take the specific fracture energies, which is the fracture energy specific to the specimen. I convert it to the real fracture energy, so which is not specific to anything, and then I perform the automatic regularization. This one will basically make the real fracture energy specific to my finite element size. I don't know if it is clear, but what I need to do is actually this. So if I switch off this one, annotate. So in all the examples that I've done before, I assume that you have the real fracture energy. In this case, when you have a specific fracture energy from an experiment or from a national code, it is the same thing in this case. What they gave you is the GT, which was specific to the specimen. Okay. What does it mean? It means that they measure something like this. They measure a stress versus displacement jump. Oh, we have something in the chat, sorry. Okay. So they measured a stress versus a displacement jump over a specimen. Okay. And this one was the real G. And then they divided the du times the height of the specimen. And then they obtained another curve with the epsilon here. And this one was the GT of the specimen. This one means that the area that they gave me is specific to the specimen. What I need to do is to go back to the real G. Now it's very easy because the real G is actually the GT specific to the specimen times the characteristic length of the specimen. Okay, in this case, this is 300. Okay, now in my case, I have a concrete, which has, let me open the calculator. Okay, so I have 0.00 for tensile fracture energy for 6 times 300, and is 0.138, and I put it here, 138. And do it the same for compression. It is 0.176 times 300. And I have 52.8. 52.8. Okay. Once I have the real fracture energy, now I can switch on automatic regularization. And what it will do basically, my material model will take this G and it will compute a small g, so a specific fracture energy, but specific to my element, which will be G over LCH of the element. Now, if you develop this one will be equal to GT specimen times LCH of specimen divided by LCH of the element. Okay, So as you can see, I'm basically first deregularizing the initial fracture energy. So I'm going to the real fracture energy obtained from by the experiment, and then I put it inside my model. Okay, and then with the automatic regularization, I will obtain a specific fracture energy correct for my element. Okay, I cannot input the initial one because the initial one is specific to the specimen. Okay, so I do this, and I think that I can obtain a good result now. You will see that I'm not going to obtain a good result actually. Then I will explain the reason for this. So I press OK. I run the analysis again. So once again, the initial slope is correct. Then I reach the peak point. And then let's see what happens now. Now it is not as brittle as before, but now there will be a problem. Actually, it is not falling now. And if you look here, you can pretty much understand what's going on. I zoom here. You will see some problems here of convergence. And in this case, you can already understand what is the problem. So I performed the concept of fracture energy regularization, but this kind of problem is similar to the first one. It is a constant state of stress, more or less. It's not like the Truss, but it's pretty much like a constant state of stress. So it's very difficult for my model to understand which element should fail, because my entire concrete cylinder, except from the Poisson effect, is going under the same state of stress. So as you can see here, you see small jumps because an element is breaking, but also the next one and the next one. So all of them are dissipating energies. While in reality, you can see that there is a clear fracture, a diagonal fracture, like a cone kind of fracture. So this is basically the problem. I can keep on going. Ultimately, it will fall, but it will take a lot of time because all the elements are dissipating. Instead, in real life, I will see a crack. So only few elements along a crack will dissipate energy. Okay, so let's go to the output and let's see what's going on. So we go to the output of strain-localization. So if I look here, the displacement seems pretty smooth. Okay, and if I look at the damages, I see a damage, a positive and a negative damage, which is very distributed. Okay, so I cannot see any crack actually. Why? Because the state of stress is pretty much uniform. Okay, well, there will be a difference here at the top and here due to the Poisson effect, but it's pretty much uniform. So here we should use the same concept of assigning random imperfections. Now, in the first example, it was a benchmark. So I said, I want to make the first elements weaker. Now here I want to apply a more statistical approach, like in STKO, we have a material called, which is under here, material ND. It's not a real OpenSys material, it's just an STK automation. And it is under Asdea software. It's called randomized material wrapper. Okay. It's just a simple wrapper that takes a source material and then the randomizer type in the current model, in the current version, it can be only from a table. And the table is an RMT file format. I will explain you what it is. But basically, you can put here the name of the file that you can use for randomizing this material. The name of the file should be in the same folder. In my case, it is here. Where is it? Here. Now, creating this kind of file manually is very complicated because you have to say how many different materials I have, what are the parameters that I'm going to change. In my case, I'm going to change the peak strength in compression, the strength in tension, and the Young modulus, and then how many sampling points I have in space. So it's very complicated. Okay, so the first material has this FCP, this FT, this A, and so on for 20 materials. And then I have more or less 1,000 sampling points. Okay, and each sampling point has the coordinate x, y, z, and the material tag 1 to 20 in this case. Okay, now you may say, okay, but how can I generate this one? Well, I can give you a simple tool now. Tomorrow you will be able to download this folder, and here you can find the Gauss random map table maker. It's a Python file that you can load here. Okay, you can add the folder where you have your file. You open the file, which is Gauss random material table maker, and basically you can choose. You can put the mean value of your compressive strength, then the standard deviation. This alpha here is a correlation factor for the spatial distribution of the uncertainties. And then you can put the tensile strength and Young modulus of your material, okay? Then you have to put these other two numbers. This one is the number of sampling you want to generate these random materials. And I said, don't make it too large, because actually I will generate a sampling matrix, which is n by n by n. So pay attention not to put a very huge number. Otherwise, you will run out of memory. So keep it as it is. 150 is fine. You can bring it up to 200. Don't try to use 1,000 or tens of thousands, because it will blow up your memory. This kind of approach will generate random materials, and you will see from the image. And actually, I want to show it like this. With known, you will see, or let's start by 100, for example. This one will generate a huge number of material, actually n by n different materials, but they are too much, okay? So I want to group them in groups. That's why I created this variable called n thresholds. This one basically say, I don't want n by n material, but I want only, I don't know, 20 different materials. So I want to group them by similarity in 20 groups, okay? Then when you run this one, you have to select one solid, otherwise it will give you an error like this. Please select only one solid geometry. So you repeat it, you select this geometry here, you run this one, and what you will obtain is a matplotlib that is saying that it generated, here there is a preview. Okay, then this drawing will go away, but basically there is a preview showing the distribution of the different material properties in space. And this one instead is the distribution, is the Gaussian distribution of your properties. It was 34.5 of a mean value with a 3 standard deviation, and this is what you get. After, well, this one is the Gaussian curve, and of course I group them in 20 groups, okay? So you have 20 different materials, which are these candles here, and you can see that they follow the Gaussian distribution. Now, what it does is that you can see this here, it gives you a preview, but it also generates a file, which is this one. As you can see, it has been generated now, okay? It generates a file according to these properties that you gave, and the mesh that you created. So every time you create the mesh, you can run this file, and it will create the random material table for you, okay? So ultimately, you will be able to have a material model, but of course, when you change it, the drawing will go away, but it's not important, it was just a preview. But now it generated this random material table. And now what you can do is that you can create the material wrapper, and instead of using this one, select, I can drag and drop the randomized material. So this one will basically take the initial material properties, take the random material randomizer, and it will assign to each element, not the real material, but the randomized material, okay? Now let's see if this can help the solution. The mesh is already partitioned, fine, and let's run the analysis. If you remember before, we were not able to generate localization. Let's see now. So the response at the beginning is the same, meaning that we changed the material properties, but the mean value is the same. So we didn't change it randomly. Okay, so the initial response is the same, it's still stable. Up to the peak is the same. And then here you can see, well, sometimes it can be slightly smaller. It can increase a little bit because it depends on the distribution of these properties. If you decrease the standard deviation, of course, this one will be more similar to here. And now let's see if it goes flat or we can see some softening. Okay, now you can see that it started softening, not exactly at the place where we expected, and now we will see why also. But it's better than before, okay? So it is a slightly more ductile than what we expected, but ultimately it managed to form a localized crack. Now let's see what can be another reason for this. But as we said, so we applied two concepts now, the fracture energy regularization, which made the solution not like extremely brittle as before. And we applied random imperfection to trigger localization. Now let's see, first of all, what's going on in the output. If I reload this one, you see now I can see a localized damage, okay? Which is like this one. It seems fine, okay, like the shape of the damage, but it is more ductile than what expected. If you can see here, the top and the bottom part are not moving at all, okay? Why? Because when you do this kind of modeling, it is also very important to model the boundary condition properly. So here, what I used in the contact, where is it? Actually, the solution is already fine because you cannot expect to obtain exactly the same solution. But here in contact, I was using 0.5, which is the friction coefficient, which is quite high. Is the friction coefficient of concrete on steel. Okay, but actually, when they do this kind of models, okay, let me just read the question. Can we understand the Gauss random math table as making each element math forming a Gaussian distribution? Exactly. Exactly. So basically what I'm doing is that instead of using just one material, I create 20 different materials in this case, the number given by the user, distributed in space in such a way that all these material models weighted by the volume of each element of the entire model, they respect that Gaussian distribution. Okay, so you're right. That's why the solution is so stable at the beginning. This is not just a random distribution of properties. In this case, it follows a Gaussian distribution plus a particular fractal distribution in space. But of course, you can use any other equation. Here I was using the Gaussian distribution, some equation given by on the internet, but you can find any other, you can use any other procedure, okay? You can do the same thing that I did here, and then all those samples are written into the random material table file, okay? But if you look on the forum, I use the same concept, for example, to create soil layers in soil problems, okay? You can put just some points manually, and you can create different layers. So you can use in this case, as a Gaussian distribution, but in any other way to define different material in space. So it's very versatile. Now, as I said, it was fine. It was enough to trigger localization. The solution is not yet what I expected, but probably there is some mistake somewhere. As I said, when you look at the output, you can see that now there is the localization, okay? But the bottom and top part of the concrete are very stick to the steel plates, because I used probably a too high contact free friction coefficient. In fact, here I was using the friction coefficient of concrete to steel. But actually, if you go on the website, you can see that they typically use Teflon sheets to reduce the friction between concrete and steel. So if you look at the Teflon friction coefficient, it should be something like 0.04. Okay, and it is the same 0.04 for friction to steel. I didn't have time to find the friction coefficient of Teflon to concrete, but I think it's the same because Teflon to Teflon is 0.05, Teflon to steel is 0.04, so sorry, 0.04 and 0.04 Teflon to steel. So I assume that Teflon to concrete is pretty much the same. So let's try to change it, 0.04. Can you please repeat how the 20 material properties are assigned in space? Yes. There is a function here. Basically, the point is that I can actually show you what happens when I change this parameter. So the amount of materials that I generate here, distributed on my elements, they follow a Gaussian distribution, okay? And this is regarding the amount of material. Then there is a distribution in space. The distribution in space, then I will send you the link to the paper that I used. But if you don't use any distribution in space, you will see something like this. Let me put a very small number here, like 1.5, for example. Let's see what happens. I have to select one solid. You can see now that they still follow a Gaussian distribution, but they are very random in space. They are so random that they do not resemble a real distribution of material uncertainties. And when you make something so random, okay, without any spatial correlation, it is like a very anisotropic material that tends to be isotropic because when the mesh is very fine and the random distribution are not correlated in space, it is like not creating any imperfection because the imperfection is so small and so dense that it's like a uniform distribution. So what it does is that it tries to group these uncertainties, these different material models, by proximity using a spatial correlation. I think the formulation that I'm using here follows a fractal noise like the ones that you can find in clouds or in material properties, and you can change it by this number. Like if you can make this correlation higher by increasing this number, like if I use 2, you see here, if I use a larger number like 3, so this one actually depends on the size of your problem, but you can do some tests. Like if I use 3, it was fine. For this kind of, you can see here that now it makes sense. I was using 3.5. If it is too large, like 5, for example, see, probably it is too smooth for this kind of problem. It is like a noise. Now I don't remember exactly the name, but I will find the paper that I used for this implementation and I will send it to you. So for this kind of problem, 3.5 was pretty fine. Okay. Perfect. So basically what they do is that, yes, and then they are assigned following, like if you want to see the assignment, you see the form shape here, you can see the physical property. Now they don't have one single property. They have this kind of random property assigned in space, okay? Following the same distribution that you see here in the preview. Okay, so I repeated this one. What I was saying, oh yes, now I need to redo the analysis. So let me go back to surface color map and a deformation of 10. Okay, so you see this cone shape is fine, but the two parts are sticked, like they're creating an extra confinement, which is not so real and probably is the cause for this kind of ductile behavior. Okay. Now let's try to instead to use the friction coefficient of Teflon to concrete, which is 0.04, much smaller. And let's try to run the analysis again. Let's see if we can improve the solution. You see here, now it's much better than before. Now, of course, it will never be perfectly equal to this one, because to have a perfect solution as this one, you have to use a constant state of stress, a perfectly constant state of stress. This is not possible because it is a three-dimensional problem with contacts, very complicated. But the concept is that computing the real fracture energy, so the one that you have here, specific to the specimen, scaling it so that you obtain the real fracture energy from that specimen, then you apply automatic regularization. You add some imperfections and you play on the boundary condition. You can see that this kind of model, which seems very simple, is actually very complicated if you don't know how to treat the problem of fracture energy, the problem of how to trigger localization in a constant state of stress, and how to correctly model boundary conditions. Because when you do a frame model, it's very easy to place boundary condition. It can be either fixed, pin, or whatever. But when you are doing a solid modeling, the boundary condition is very important. Even if you make a wrong prediction on the friction coefficient of the support, it can give you a completely wrong result. Now it is fine. Okay. Now I use the correct regularization, a correct boundary condition to resemble the experimental test, and now it is fine. Okay. Now let's see what changed in the output. Okay, now you can see before it was a kind of cone-shaped crack, which was pretty fine, but the two parts here were still sticking to the steel plate. Now if I reload this one, okay, you can see something different. Now this one, you can see that it is free to be pulled out, okay, because it can move from the initial position, okay. If I do this, okay, can localize, and it has more freedom to create the full crack here. Okay. So once again, you can see the response, which is stable at the beginning, and then the localization, and the two parts here that are free now to move from their initial position. And this one has reduced a lot the confinement given by the too high friction coefficient that I expected before. Okay, so with this is also to do a recap, you need to, when you do this kind of problems with fracture energy with strain softening, you need to use a material that possibly can perform an automatic regularization. Otherwise, you can do it manually, because it is a simple division of the real fracture energy times the length of the element. The problem is that when you have a mesh like this, when every element has a different length, how you do it, it's very complicated to do it manually. So if you have a material model that can perform an automatic regularization, it's better. So the first topic is that you have to use a real fracture energy, not a specific fracture energy. If it is possible, you have them from experimental results, it's fine. If you don't, if you have specific fracture energy from experiments, then you need to obtain what was the real fracture energy from which they obtain the specific fracture energy. Typically is the specific fracture energy times the length of the specimen. Okay, so once you have that, you have the real fracture energy, you can input in the material model, and you can switch on the automatic regularization. So this is the first part, to ensure that the amount of dissipated energy is independent from the mesh size. Then the second problem that you have to take care of is that when you have problems which are constant, constant, very uniform in terms of distribution of loads, distribution of material properties, like the constant state of stress that I showed before, or this one. You need to solve the problem of bifurcation of the solution, because the numerical model in a very uniform setting, like a uniform distribution of strength, a uniform distribution of load, the numerical model doesn't know which element should fail. So why the crack should form here and not here, for example. To solve this problem, you can add imperfection. Okay, so in this case, for example, the imperfection was located in this area. If I generate another random material table, probably the next crack will form here. But the point is that the entire solution now is able to find a path for the crack. Okay, so this was the second problem. And a third problem that I didn't have time to explain it to you, but now you can do some tests here. The mesh should be sufficiently fine. Because, for example, here for concrete, I know that I have a kind of cone-shaped crack. But if I use a very coarse mesh, I will never be able to capture this kind of crack. So the mesh should be sufficiently fine to capture the crack that you want, of course. Okay. So I hope you enjoyed this webinar. And if you have any question, is element deletion possible in combination with this type of analysis? Yes, element deletion is possible. It's not so easy in OpenSys because it's not automatic. It can be done, and if you want, you can watch this webinar. Let me find it. We have a webinar where I explain how to do it, and there is also an example. You need to use some Tcl code because there is not a built-in function. You go here, STQ Academy. You go on. What is it? E-learning courses, and then you have the course on nonlinear time history analysis. Okay, in this webinar I explain how to perform nonlinear time history analysis or in both implicit dynamics and explicit dynamics, which is this one. And in the explicit dynamics I was simulating the blast, an explosion of a masonry wall. And in a masonry wall, I was deleting the pieces of element according to a stretch factor. Now you can download the file here. You can watch the webinar here. And toward the end, at the beginning, I was explaining the standard time history analysis of a bridge. And then I moved to the explicit. I want to show you the, oops, it's not this one. This one is what we are doing now. Linear time history analysis. Okay, this one was still the bridge, and then I was explaining here the masonry wall, the element deletion. I just want to show you the animation here. Okay, here you can see the first deletion of the element. And then when this analysis will start, you will see that here, okay, as they move or as an element reaches a certain criterion that can be a damage-based criterion. In this case, I was using a deformation criterion. When the element was deformed over a certain limit, I decided to remove it. Okay, but pay attention, and I will tell you that it is not so easy. It is quite complicated. You can watch this one. You should do explicit dynamics, because when you remove element, you have pieces falling down, so the stiffness metrics will be singular. You need to use explicit dynamics. It's not so easy, but if you want to understand how it works, you can watch this webinar. Okay. So yes, it is possible, but be prepared to work a lot on it. Okay. About the next webinar for reinforced concrete shear wall, fiber-based modeling will be discussed. Yes, but what we will do is basically, we will show shell models, solid models, and the beam truss model, and also the multiple vertical line elements, so the MVLAM element in OpenSys. And that actually is a macro element that contains several fiber beam elements. So it's similar to the fiber beam approach in this sense. I will not do a shear wall with a single beam element, because actually it's not convenient, in the sense that when you create a beam with a fiber section, it can only represent bending problems. Okay. Then if you want, you can aggregate shear with the shear aggregator, but the shear will be completely uncoupled from the bending, at least at the constitutive model level. So it is not convenient to model a shear wall with a single beam fiber element. But yes, I will show fiber-based shell elements, so the layer shell elements, solid elements, and the multiple vertical line elements. Okay. It will tomorrow. You will have all the information and the invitation for the webinars. It will be a 4-day webinar series where I will start with the shell elements. Then I will move to solid elements, the truss model, the kind of strut tie model, and then the multiple vertical line elements. It will start in July and it will end in August. And finally, in September, we will have a final meeting for roundtable and discussion, okay, and a comparison among all the models that we can use in STK and OpenSys. And that will be an interesting webinar series.
Massimo, this is Joel Conte. Can I ask you a question verbally?
Sure.
About what you presented. So yes. Do you know if material labs, when they would test a cylinder of concrete, for example, in the US, right? It's a cylinder. In Europe, I think it's a cube. Do they always, when they give to the client, the stress strain curve, do they always use as gauge length, the total height of the element? Or do you know if there are cases where they define internal point to the specimen, and they use this gauge length?
No, there are cases. There are cases. In fact, this is what I'm going to show you now. Just a second here. I need to share the screen again. When I was talking with this user on the forum here, this is one of the things I told him. I told him, yes, the specimen size, the specimen characteristic length is not necessarily the total specimen size. I've seen that probably for the ReLEM, they measure the displacement of the top to the bottom. In some other experiment, they measure a smaller difference. So the topic is that you should be able to they should give you the stress strain curve and the distance they use to compute the strain. Okay. Now, in this example, they were using a very small distance, but typically it's comparable to the entire height. It's comparable to the entire height simply because I don't know. I took this one from the website, but this is very, very strange because typically the fracture in concrete is diagonal, and it is a certain inclination which is similar, not to the entire height of the cylinder, but pretty similar. So in general, the distance between the LVDTs should be slightly larger, but there are cases in which they are smaller. In other cases, they use multiple points to measure them, and they give you an average. So it's not so easy to answer, but the point is that they should give you both information. So the stress strain curve and what is the size they use to compute the strain. And so you can go back to the fracture energy. But the topic is that even if it is not the entire H, it can be smaller, it can be 1/2, it can be 2/3 of H, but it cannot be larger than this one. So you have a maximum bound, which is this one. And as you can see, this kind of problem, they are very aleatory. The fracture energy is a very aleatory variable. So even if you make a small mistake by taking the entire height instead of half of the height, it's not a problem. The important thing is that you do not make errors of order of magnitudes. Like in his case, it was using 0.1 instead of 50, okay, which is almost 3 orders of magnitudes. But if instead of 50 you use 40 or you use 100, it is not going to be a huge problem, okay? Now in this case, it was a benchmark, so I tried to capture the curve as close as possible. But it is a very aleatory variable, so I would not pay so much attention. But true, if they should give you something, it should be the stress strain curve and the distance they use for computing. Because at the end of the day, they use a distance for computing the strain. So they should be able to give it to you.
Yeah, I think that one reason why they would not use maybe the whole height is the awareness. I've heard experimentalists talking about the fact that these top and bottom plate, they confine the concrete. So you don't have a uniaxial state, you don't have a uniaxial strain state close to the plate. So they want to be a certain distance below. And maybe a second question, Massimo, because now the question of the uniqueness of the physical solution. Let's imagine that there is a certain type of concrete. They do a test on a cylinder, maybe 300 millimeter tall and 150 millimeter diameter, right? Mm-hmm. And let's say they give you the length, the gauge length, maybe instead of 300, maybe they use 200, right? And now they take the same concrete and instead of 300 by 150, they would do a 200 by 100, mm-hmm. right? And so, I don't know if you know where I'm going. You would have two different physical, regularized, right? Regularized by two different physical solutions. What can you say about that?
Yeah, no, but it's perfectly true. I mean, what I said now is that we have this kind of dependency on the mesh size on the numerical model, and this is wrong. We have to solve this kind of problem. But also in reality, when they give you direction for creating these specimens and they decide a certain size, is that because they know that this size should be sufficiently large to capture the fracture process zone, but should not be extremely large, otherwise it will be brittle, because the size effect is also happening in reality. That's why they choose something like this. For example, if you choose a very small specimen, it will be very ductile because it will be very confined. If you choose it very, very slender and very high, you will have kind of buckling problems and stuff like that. So they typically choose dimensions like this just to avoid this kind of non-uniqueness.
Yeah. Okay.
You're right. If you choose a cylinder which has, for example, the same diameter but half the height, it will be much stronger, because the size effect there is saying that you choose a height of the cylinder which is larger than the typical fracture cone of the concrete with that diameter.
Yeah, then the size effect is kind of a third issue, right? Yeah.
Exactly. The size effect of the real material. That's true. That's another problem. But that is a problem that happens also in reality. So it's not strictly related to the material model. It is more a problem that they have when they do material testing. Of course, for example, if you think about concrete, you already have a certain size limit, which is the size of the aggregate. So it already tells you if an aggregate is the order of centimeters, you cannot make a specimen which is the order of centimeters. It should be 1 or 2 order of magnitudes higher. That's why they choose this kind of dimensions. So that's perfectly true.
Yeah, thank you.
Welcome. Yeah, this is a very complicated problem. That's why we decided to make this kind of webinar, because we have seen that many users use concrete, but they do not take care about this kind of problem. It's very complicated. It's not something that you can solve quite easily, but following these kind of guidelines, at least you are more aware of what to expect from this kind of analysis. Okay. So if there is no other question, thank you for participating to this webinar. Don't forget to sign up for by tomorrow for the next webinar series about reinforced concrete shear walls. And of course, those webinars, I give for granted that I will not repeat the topics of fracture energy.
Hello.
This kind of problem will be there. Yes.
Hi, Massimo. Can I ask question?
Sure.
Sorry. A little question. I am trying to calibrate the shear wall with damage TC, but I only I divide like that, like you making some webinar. The shear wall, the solve. I don't know if you understand, but the solve of the shear wall and the boundaries really. So the boundaries, I put the option of auto regularization and the solve no, and it it provide me the best results. It's logical that, or the same thing, but in the other way. I mean, solve with auto-regularization and automatic from its TKO, and boundaries without a regularization, auto-regularization that the software provides.
That boundaries without regularization, you're talking about the boundary beams.
Yeah. The boundaries are beams.
Understood correctly, you obtained a good result using the fracture energy regularization in the shell shear wall and no regularization in the boundary beams.
Exactly.
Probably this was fine. You know why? Because they gave you the specific fracture energy computed over a certain length, and then you discretize the beam with a size which is close to the plastic inch size. In that case, the regularization is not going to do anything in that case, okay? So probably that's the case. Sometimes also when you have a lot of steel, the regularization is not going to be a huge problem because you have a lot of steel there. So it really depends. But if you obtain the real fracture energy from an experiment, you should always use automatic regularization. Now, in your case, probably it's fine because they gave you a specific fracture energy which was already calibrated for that finite element size. So it can make sense, but it's not a general rule, okay?
Okay. Thanks a lot. See you, bye.
See you, bye. Okay, so thank you everyone and see you to the next webinar. Thank you again.